Yesterday, we started talking about chemical bonds. Generally, what is a chemical bond? Andrew, go ahead.
Like the combination of two atoms to form another element of something.
Okay, instead of an element, let's go, we call it a compound, right? Okay, so it's the formation of a compound from two elements, right? What holds those elements together? There's some kind of...
Valence electrons.
Not exactly. Jillian? Some kind of attractive force that has to hold those atoms together.
What is the force?
Well, that's what we're going to talk about today, all right?
Oh.
And actually, the answer to that question is it depends on what kind of bonding we're talking about. Okay. All right. So, why does bonding happen? What's the reason why these atoms will join together and form new compounds? Trey.
They're trying to reach a low energy.
They're trying to reach a low energy state. And right at the end of class yesterday, we said that a low energy state for an atom looks like what? Or what does an atom look like that is in a low energy state, Trey? It has 8 valence electrons. It's not that we're balanced between protons and electrons. An atom is in a low energy state if it has 8 valence electrons. And that idea we call what? What is the idea that 8 valence electrons is a stable situation? Jillian? Octet rule, right? The whole OCT prefix, right? Octopus or octagon, right? 8 electrons are 8 valence electrons. Okay? Good there. All right. Yesterday, we drew a bunch of Lewis structures. And we talked about that Lewis structures show us the valence electrons that each atom has. We only look at the formula and then the valence electrons. We don't worry about anything else because the valence electrons are the ones that deal with bonding. Okay? How do we determine how many valence electrons something has? Where do we look? John, go ahead. Highest energy level, yes. And then yesterday we kind of talked about a way that we can tell real quick how many valence electrons something has.
Electron configurations.
Yes. Did we go through
Group number.
group number, right? That if we look at our periodic table, right? Good. Let's look at the whole periodic table. And let me grab this here. Go here. All right. That's not what I want. There we go. Right? That this is one valence. These atoms have one valence electron. These have 2, 3, 4, 5, 6, 7, 8. Okay. Helium doesn't have 8. It only has 2. Okay. But we'll see in a second that that's all right. Okay. All right. Good here. Now let's talk a little bit about how these valence electrons go into becoming stable. All right. So let's take a look at. Let's not do sodium. Yeah, we'll do sodium. Okay, so here's sodium. Okay? So we look on the periodic table, and we find sodium. We find out that sodium's atomic number is what?
11.
11. Right? 1s2, 2s2, 2p6, 3s1. Right? And we don't have to write this electron configuration, but how many valence electrons does sodium have?
1.
Just 1. There's its Lewis structure. Okay? All right. Trey, you told us before that, gotcha, yeah. You told us before, Trey, that in order for an atom to be stable, what has to be the case?
It has to have 8 valence.
8 valence electrons. So, this atom of sodium has 2 choices, right? What's one way that it could get to 8 valence electrons, Trey?
It could gain 7.
Okay, it could gain 7 electrons, right? It's only got 1 valence electron right now. If it gains 7, guess how many you'll have? 8, right? Is it going to do that?
No.
No, it is not going to do that. Why not? Captain, go ahead.
It would be easier to just do 1 and then
Why is it hard for it to gain 7 electrons?
because it'll take more time.
True. What starts happening when it starts gaining all these extra electrons? Andrew.
The atom becomes unstable.
The atom becomes unstable because what do all those electrons do to each other, Andrew?
Repel.
Putting 7 extra electrons around an atom makes this really, really, really unstable. Because all those extra electrons start repelling each other, and they start repelling the electrons that were already there. It just doesn't happen. Okay? It's not a way that it goes. But, Catherine, you kind of took our next step. What could this sodium atom do? It could lose 1. If it loses 1 electron, it's going to lose the valence electron, which takes it to look like this. And now it gets rid of this, right? Before we do that, let's go back here, right? What was the highest energy level in sodium when it was written this way? 3 is the highest energy level. And there was 1 electron in the highest energy level, 1 valence electron, right? But if it loses this valence electron and this goes away, now what's the highest energy level? The second energy level is now the highest energy level. And how many electrons are in that second energy level? 8. So how many valence electrons does this sodium atom have now? 8. Is it stable? Yeah. Okay? Good there? If we go the other way, though, let's take a look at oxygen. Okay, Catherine, go ahead.
Wait, but then would it still be sodium?
Good question, Catherine. Right? So, 30 seconds. Talk with the person next to you. Is this still sodium? Discuss. Go.
I don't want the microphone to hear my conversation. Oh, I think I'm on to something. We've been surprised that could, like, or if it has, say, 4, could make an atom that has, like, 2 electrons, or an atom that. How can it just, like, let go of 3?
We'll get there.
I'm
All
just
right,
too advanced
here we
for
go.
this class.
All right. Now, don't be a chicken, okay? Don't be a chicken and vote. Yes or no? Yes, it is still sodium. Show of hands. Don't be a chicken. You got to vote. One or the other, okay? Yes, it is still sodium. No, it is not sodium anymore. All right. So, yeses. People that voted yes. Why did you say that it is still sodium? Julie, go ahead.
Because it
Still
still has the same number of protons.
has the same number of protons, and protons are what determines what kind of an atom it is. So the answer is, it is still sodium. But it is not, hey, it is not a sodium atom. We call it something else that I'll tell you about in just a second.
Wait, but how do you know that it's still
Because the only change that we made, right, Jillian, is what happened. Not Jillian. Catherine. The only change that we made to that sodium is what?
Oh, it took away the valence electron.
It took away an electron, right? We didn't do anything to the nucleus of that atom, right? So it's still sodium, but it is not a sodium atom anymore. And we'll talk about what it is in just a second, okay? Nora, go ahead. We'll talk about what we call it in just a second, okay? It's not an isotope.
Ion.
Isotopes have different number of neutrons,
Is it
okay?
ion?
It's an ion, yes. Go ahead, Nora. Hold on, we'll get to that question, okay? All right, so let's talk about oxygen, okay? Oxygen. You look at the periodic table, atomic number of 8, 1s2, 2s2, 2p4. How many valence electrons? 6. 1, 2, 3, 4, 5, 6. Okay? How many many valence electrons is it looking for?
8.
It's looking to get 2.
Wants 8.
It wants 8, so what is it going to do?
Get 2.
Get 2, right? So in this case here, if it picks up 2 electrons, it's good to go. All right? Good there? So, getting back to our outline. Okay? Can't remember if we did this one yet. Okay? Atoms are trying to get to 8 valence electrons, and they will take the shortest route to get there. That means that some atoms will gain electrons, and some atoms will lose electrons. Okay? Go ahead.
What do they do if they have 5?
5, well, what's the shorter way to get to 8?
3.
5 is not the number you want to ask me about. What's the number you want to ask me about? You want to ask me about? 4. The answer to that question is, wait till next week, Catherine, and then we'll talk about that. Okay. So the answer is that
Yeah, I don't think more.
it doesn't gain or lose electrons, Catherine. It shares them with other atoms.
You spelled losing wrong.
Losing.
Oh, I got it right.
All right.
What did he spell wrong?
Losing. It's only got 1 O in it. So. But the problem with that, Maura, is that losing is actually a word. Like it doesn't
It
show up on,
is.
doesn't show up on spell check. So you know. All right. What we find out is that atoms will gain or lose electrons to have a full outer shell or a full valence shell. Metals are going to lose valence electrons in order for their electron configuration to look like the previous noble gas. If you remember, right, we drew a Lewis structure for a noble gas yesterday. It was neon. And neon has 8 valence electrons. So if we have 8 valence electrons, it's stable. So now, sodium, after it loses that electron, its electron configuration looks like neon, but it still has 11 protons. Nonmetals are going to gain electrons. If we were to fill in those 2 electrons on the oxygen that we just drew, its electron configuration would look just like neon. Again, it still has 8 protons. It's still an oxygen atom. Sorry, it's still oxygen, but its electrons look more like neon because that's more stable. Right? There are some exceptions to this rule. For example, if we look at lithium, okay? Lithium only has, oh, goodness gracious. Lithium only has 3 electrons. So it looks like this. And it has 1 valence electron, right? Where is lithium on the periodic table? Is it a metal or is it a non-metal? It's a metal. It's way on the left-hand side. So what's it going to do with valence electrons? Lose them. So it's going to lose this electron, right? And now, it only has these 2. But, remember, in energy level 1, there are no p orbitals, right? It's just an s orbital. And how many electrons can the s orbital hold?
2.
Just 2. This is full, even though it only has 2 electrons. Okay? So some small atoms might only need 2 electrons in order to be stable, not because they're an exception to the rule, but they're full with only 2 electrons. That's the important part. Okay? Good there? All right. Why are our noble gases important? Noble gases are unreactive. They don't form compounds with other elements. Why? Because they are already stable. They already exist in a low energy state. Remember we talked about the idea that atoms form compounds with each other in order to get to a lower energy state. If something's already in a low energy state, it doesn't do anything, it just stays there. you this example yesterday, right? If this ball, sorry, I just writing. If I take this ball and I roll it along the table, when it reaches the edge of the table, what happens? It falls. Why? How much energy does it have on the floor versus on the table? Less energy, right? But if it starts off on the floor and I start it rolling, right? Does it do anything? It can't get any lower than the floor, so it doesn't fall. Does that make sense? If something's already in a low energy state, it doesn't form compounds to get to a low energy state. It's already there. Okay? The highest energy level of noble gases is full. Therefore, it will not form bonds. And that's why when we look at the electron configuration of atoms that have either gained or lost electrons, they will look like the electron configuration for noble gases. All right, are we ready? Ready to put this into practice? Okay, first thing I need you to do, next thing on your outline, it says, how does a bond between sodium and chlorine form? And letter A says, draw Lewis structures for sodium and chlorine. So, use your periodic table, find sodium, find chlorine, and draw me Lewis structures for sodium and chlorine.
Oh, sodium's Na. Oh, you don't have to do the whole electron. Oh yeah, that's right. The one is one.
Yeah. You just do that valence thing.
I know, I'm doing it. I wanted to do it.
All right. Do they look like this?
Just
Hopefully?
Like, just
Yeah.
Like, yes.
Okay.
Except my dots are.
All right. So, starting off, how many valence electrons does sodium have? One. Is sodium a metal or a non-metal? Metal. That means what is it looking to do with that valence electron?
Lose it.
Sodium has one valence electron. It's looking to lose it. On the other hand, right, chlorine, 7 valence electrons. It's looking to gain 1. Drop down to letter C in your outline.
Alright.
All right.
So is it
So-
gonna take? Is it gonna take it?
So, right, Maura, are you ready, Maura? Brace yourself, okay? All right. I'm just saying, okay? You guys might want to consider after today's class, just call your mom and say, Mom, I'm ready to come home because I'm not going to see anything better than I just saw. Okay? All right, ready? Here we go. Maura, ready?
There's energy.
Yeah.
Here it goes.
It's gotta be.
Oh!
Whoa. I know it's not me. Thanks, Rhea. Just Rhea's complaining because it's not me.
Yeah, it's crooked and like, oh. OCD kicking in.
All right. So
It's stolen.
let's talk about these, right?
It's
Okay. Metals. We just talked about that metals will lose valence electrons. When metals lose valence electrons, they end up with more protons than electrons. If an atom has more protons than electrons, what charge does it have? It has a positive charge. And when we end up with something that has a positive charge, we call that now, it is not an atom anymore, it is a cation. It's not a cation, it's a cation. Okay? So, Catherine, back to your question from before. That sodium is still sodium, but it's not a sodium atom anymore. It's a sodium cation. Does that make sense? It's still sodium because it has 11 protons, but it's a cation because it has now only 10 electrons. Okay?
So like they can move around, but
Yep.
they'll still be the same. So
There's
chlorine's
still
the same.
sodium. It's still chlorine, but we'll see here it's not a chlorine atom anymore. Okay? It's called now an anion, not an anion. Okay? It's not an anion. It doesn't rhyme with onion. Okay? It's an anion. Nonmetals will gain electrons. Once they gain electrons, now they have more electrons than protons. If they have more electrons than protons, they have what kind of a charge? Negative charge. That atom that has gained electrons and now has a negative charge is called an anion. So not an anion, anion. In general, any atom that has a different number of protons and electrons is called an ion. Some ions are positive. Some ions are negative. How do we create a positive ion? Go ahead. Lose electrons. You don't gain protons, you lose electrons, right? How do we create a negative ion? Gain electrons. Just like in the last unit when we talked about something that gains a charge, right? Protons don't move around. Electrons move around. Okay? All right, good there? Okay? So, now, after this transfer, right? Sodium now has 11 protons and 10 electrons. It has a positive charge. It is a cation. Once you have filled out on your outline number 1, little a and little b, right? See if you can fill out number 2, little a and little b, as it relates to the chlorine atom. See if you can figure out what number 2, small a and small b should be. Come on, number 2, Trey, come on. What are you dealing with number 2 there, Trey? Okay. So chlorine now has 17 protons, right? Because that's chlorine's atomic number, but it has 18 electrons now. Right? Because it gained one from the sodium. Therefore, it has a negative charge, and it is called an anion. All right? Mora, any guess what's going to happen next?
No.
Come on, Mora.
I don't know. Are the dots gonna move again?
No.
It's too bad.
They like explode.
Ready? What charge does this have?
They form together, they go NaC.
What charge does
Wait,
this
they
have?
mush. They mush.
Ready?
So they mush because sodium chloride. Got it.
Ready? Ready?
Sodium fluoride. We're so proud of ourselves.
The negative charge on the chloride anion and the positive charge on the sodium cation attract each other and form what we call an ionic bond. Remember, an ionic bond, or any bond, is an attractive force that holds atoms together. Right? So Andrew, you asked before, what is the attractive force? So what's the attractive force that's holding these atoms together? Are you with me or are you trying?
Yes.
Okay. So what's the attractive force that's holding these atoms together? You don't necessarily have to name it. Charges, right? Opposite charges attract one another. Does that make sense?
Yes.
Okay. All right. Good there? Let's finish this off. Negative charges are attracted to positive charges. We know that from the last unit, right? And that means that negative anions are attracted to positive cations. The result of that is an ionic bond. Ionic bonds are the attraction of opposite charges. Ionic bonds happen after the transfer of electrons from a metal to a nonmetal, and then it causes them to form ions. The ionic bonds happen after the transfer of electrons from a metal to a nonmetal and the formation of ions. All right, good there?
Yes.
When you are done filling that out, if you would please open your book to page 159. Open your book to page 159. Don't worry, Christine, we got some time left.
Did you ignore him? Yes.
Whoa. 159. 159.
The graphics of the moving really helped me learn.
It's supposed to. All right. Here's what I want you to do. On page 159, I would like you to read page 159 and then page 160, just the paragraph at the top. So stop where it says some cation, what does it say? Some cation names show their charge, okay? Stop there. I want you to read page 159, the first paragraph on 160. When you are done, just put your pencil in your book and close your book so I know that you're done. Go. All right. Now that we have completed the reading selection, how many of us are familiar with the concept of Cornell notes? What?
brother complains about them every day.
All right, so first, let's talk about what a Cornell note is, okay? A Cornell note is a way just for you to organize some topics, organize some details, organize some studying. A lot of times we will do it off of a reading selection. So we'll help you do it, read something, and then pick out the big ideas, okay? First, organization. Oh, not that way, this way. Okay. Your paper generally gets divided into 3 sections. They don't necessarily have to be the way that they are on my sheet, okay? First off, these are your Cornell notes. They're not my Cornell notes. I will not grade them. I will not collect them, okay? Yours don't have to match mine. They have to work for you. So, 3 sections. A skinny section over here on the side, a bigger section over here on the right side, and then a couple of lines down at the bottom, or a little bit of space down at the bottom. Okay? Like I said, if you want to fold, you can fold. If you don't want to fold, you don't have to. They don't have to be even. Whatever works for you. Oh, page 159. All right, so Cornell notes, 3 parts. 3 parts, okay? Actually, kind of 4 parts. One look at today. Here is an example of somebody doing Cornell notes. These obviously don't relate to what we just read, but so at the top, you got to give me a title. What are these Cornell notes about? So, based on the reading section that you just did, what do you think that maybe we should call our Cornell notes that we're doing here?
Ion notes.
Okay. Hold on.
Special.
What exactly was the section that you read about?
Cat ions and ions.
Compound names and
And formulas.
formulas. Right?
I knew that. You know how?
Good. Okay, so that's where we start. Compound names and formulas. Now, the Cornell notes have 3 parts. Okay? You don't necessarily have to call them this, and you don't have to label them this, but the small section on the left, this example calls it the Q column, or sometimes we'll call it the big ideas, right? These are your main ideas that you read throughout that little section. On the right-hand side, this is labeled the note-taking area. That's where we add details to the main ideas that we put over here on the left. Down at the bottom, summary area. Generally, what we want you to do at the end is once you've taken your cues, your main ideas, you've added some detail, now write a sentence or 2 that summarizes what you did. Okay? So here's what I want you to do. Okay?
So what notes is that?
That's that.
Well, that's a very quick question for what are those notes?
Okay.
I don't
These are just examples. All right? This is not anything that we're doing in
Okay, but
class.
what is that?
This is somebody doing Cornell notes about types of leadership theory. Okay?
Can you explain to me who this guy is?
Here's what I want you to do. Tonight, I would like you to try and do your Cornell notes for that section that we just read. Okay? We will talk about it at the beginning of class tomorrow. You'll do one more section that we have to read in the book tomorrow, and then we'll get into practicing some names and formulas. Okay? I will adjust the calendar to reflect that. Okay?
Yeah,